So today we'll continue discussing logistic regression, especially with respect to goodness to fit and connection to the other sorts of log linear models that we've discussed, like this hierarchy table of hierarchical log linear models. So we've had this idea of nested models. Some simpler model, like the independence model, sitting inside some bigger model, like the saturated model. And we've, in the context of models for multi-way tables, studied these sort of goodness of fit tests, mainly this one, right? Mainly the difference between independence and the saturated model. And I've been telling you that we can test more subtle variations on that. And that's especially easy to see for logistic regression, right? Because we'll end up getting things like where you predict yi to be some sum of an intercept and coefficients times some variables. And the nesting that happens here is just the nesting of, the simplest model just has the intercept, or the simplest model has nothing whatsoever, which would be like a uniform distribution. If you have an intercept, then that's like, you allow this p to vary, but it doesn't depend on the covariance at all. And then you keep adding in additional predictors, and every time you add a predictor, right, you have this relationship, like the simplest model is x0, and then you have x0 and x1 allowed, then you have x, or really, let's say beta. So the simplest model has beta 0, non-zero, then you have beta 0, beta 1, then you have beta 0, beta 1, beta 2. And so we get a nested sequence of models, and we can ask questions about joint significance of these parameters. By skipping over some of these, we can ask questions about sequences of parameters as we add them in and take them out. And there are a lot of more sophisticated techniques for model selection in logistic regression and in related questions that are all about, you have some huge number of predictors, you start from nothing, and you try to figure out what's the best way to choose them, right? The path through those, adding those variables, or this backward selection idea where you start with lots of variables and then you eliminate some, right? So, but it's a hard question. There's an explosion of different models, and so it really takes a lot of perspective to try to decide what model is best. So, okay, so we have always sort of what the notes calls a current model or a biggest model, and we're comparing it to some smaller model where we've zeroed out some of the coefficients. And for that, we get a difference, right? So we have a bigger model versus smaller model. And this might just be, how many coefficients are allowed to be non-zero. And then for each of these things, we get a g squared, and we get a degrees of freedom. And in the case of, certainly in the case of saturated versus independent and saturated versus everything else, the g squared on the bigger model is always just 0. And the g squared on the smaller models, whatever it is, the degrees of freedom is some maximal number, and we subtract the degrees of freedom here. And at least when we're comparing with a saturated model, these differences, so the difference between these g squares is itself the g squared for the test, right? And the difference between the degrees of freedom is the degrees of freedom for the test. And the new thing is that this quantity, delta g squared, is now a statistic that we can work with. Okay, so this is, in fact, chi squared, approximately, asymptotically, and the degrees of freedom is just the difference in the degrees of freedom. Okay, and so we can get, what does that mean? It means that any comparison that we'd like to make of a smaller model inside of a bigger model, we can actually get a significance for it, right? Probability that a chi squared with some number of degrees of freedom that we've calculated as the difference in degrees of freedom in the model is bigger than delta g squared, gives me the significance of adding new covariates or non-zero coefficients. So that's great. That means that we can not just say, well, this model seems to fit better, but we can actually say this model fits significantly better or doesn't fit significantly better. And we'll see some examples of that. And just to mention how it works in the, so I try to focus on what's going on conceptually. Depending on the software you use, it'll call these things different quantities. And some of what's the online notes are devoted to is to make sure that you're aware of the problems that come up. Right, so you want to make sure that what you're asking the computer is giving you the right g-squared, and it very much depends on exactly what you put in. But you want to make sure that it's doing the right thing. And one way to, obviously it's hard to compute the g-squared yourself, but the degrees of freedom you should be able to compute yourself. So that's one clue you can have that you agree with what they're doing. And because there's so much redundancy in all this, there's going to be more than one way to compute it. But one thing that I just want to note is that sometimes it will call this quantity 2 log minus 2 log L, right? That's what the g-squared is. So it won't show up often as g-squared, but it'll be called that in the output. So for example, in the 1 to 2 parents smoke versus neither example, if you plug this into SAS or R, you'll get some table that's like intercept only, intercept and covariates, of which there's only one because we collapsed the table. And it'll give you numbers like 5176.5 and 1 and 5147.39. Well, those look pretty close because they're big numbers, but actually, what we're interested in is not the multiplicative difference, but the additive difference. So the delta g squared here is just this number minus that number is 29.1, and there's degree of freedom is 2 minus 1. So that's a big number for 1 degree of freedom. And that tells me that adding the covariate, adding in the factor of whether or not they smoke, as opposed to the intercept only, the baseline probability when neither parent smokes, adding in a smoker significantly increases the fit of my model. And you can test, similarly, if I wanted to test jointly multiple of these, I could do that, or individually. At this point, let me mention this other statistic called this Hosmer-Lemeshow. So in this situation, in this particular example, it's not an issue, but as the number of levels, or number, like if I have continuous case, there's a whole lot of levels, or number of covariates increases, you think about the table that I would make. I have an output and I have all these different covariates. As these things get bigger, well, my sample size doesn't get that much bigger. Like if I measure a lot, if you're designing a survey or a study, often what you do is you measure as much as you can because it's expensive to get each input. And so as this number increases, the cells get really small. The cells in the table get really small. The cell counts. Let's say the cell counts. The cells are just boxes. The cell counts get really small, and that means that the chi-squared approximation will be bad. Okay, so that's something that can happen. And the Hosmer-Lemeshow statistic is a strategy for how can we measure goodness of fit even in this situation? Because though this method works theoretically, if the cell counts aren't big enough, it won't work in practice, right? So n is not close enough to infinity. And the idea here is kind of to convert n-way to like a sparse n-way table to a dense one-way. That is, I have lots of covariates. Right? If I have 10 different covariates and each one has many different levels, and it ends up that I only have, my whole contingency table out is full of zeros. Okay? that's sparse, and it's many-way. And I want to convert it to a dense one-way table in order to check the goodness of fit. Of course, that's going to be problematic because we're destroying a lot of information to do that, right? But OK, it does something for us. And the idea is that it's kind of an information theoretic idea in some sense. So you have some very high dimensional space, and it's making a prediction about this simple binary variable, right? Probabilities for a binary variable. So this very high dimensional space of possible tables is being kind of predicting or indexed by this one-dimensional interval of probability of success or failure. So the idea of the Hosmer-Lemeshow is to say, OK, take the domain of this function, probability equals 0 up to probability equals 1, and break it up into similar chunks. And usually this is around the sample size, certainly not bigger, right? So the problem we started with was that there was way too many of these things. It was not dense, so we want something where it's approximately equal to the sample size, right? Maybe a little bit smaller, same order, and then take these high-dimensional thing and just group them. So all of the different points that map to this probability, or probably in this range, we just call them one group. Group 1. All of the points that map to a probability in this range, we call another group, group 2, and so on. Okay. So we've kind of taken this table, which is multi-way, multi-dimensional, and compressed it into just one vector of groups. Group 1, group 2, group G. And then we're using this as the predictor variable, and the output as the usual independent variable.
Yes, excuse me.
Yeah.
I was wondering, so the way how to group the variable, whether based on the group lasso, or what kind of criteria,
No, it's the ones that have a similar prediction and probability.
So it's not a group lasso?
No. OK, and then, OK, so we want these groups to have approximately equal size. This is kind of a very ad hoc statistic, really. But it's something that's easy to get your software to report. And then we do a chi-squared, a Pearson chi-squared on this model, on this grouping, which is basically a simple two-way table now. And the Hosmer-Lemeshow test on this is I take a sum, I equals 1 to the number of groups, sum over observations. So I is the group and j is the observation. So yij is just whether the outcome was 0 or 1. And I subtract from that an estimate from the model, sum over j pij. So the model might be more, this is the logistic regression model. So it's more fancy than this table suggests. So in some ways, we're using a different criteria. It's like mismatched with the model. OK, this is the statistic. You compute it. It's not asymptotically chi-squared, but when g is approximately equal to the sample size, big G, the number of groups, then it's approximately chi-squared with big G minus 2 degrees of freedom.
Yes, it's also one here we're using the G minus 2, whether the 2 is the degree of, because the total degree of freedom for the saturated model is G, right? So in other words, the degree of freedom for the independent model is 2, so that's the reason we're using G minus 2, right?
Yeah, so I didn't quite understand. Maybe we can talk about it afterwards, OK? OK, so, all right, so to calculate it, what we do is we do this grouping. We want roughly an equal number of observations per group. make this statistic, which sort of by magic is sort of chi-squared, even though it's not asymptotically chi-squared. You know, it's a bit of an ad hoc statistic. It has some problems. It's conservative. It doesn't have very good power. If you change the grouping, the statistic will change. If you use too few groups, it's going to overestimate your fit. Anyway, so I just wanted you to be aware of it, but it's not something that fits very well into our general theoretical framework. The other things you can look at for goodness of fit are, of course, residuals. And Pearson and G-squared residuals. Okay, so the next thing I want to discuss is what happens when we have a multiple level explanatory variable. We have a multi-level explanatory variable. In some sense, this is a very slight extension, right? All I'm saying is, in a second we'll talk about with many, but instead of 2 by 2, it's 2 by 3 or something, right? Or 3 by 2. So in the smoking example, right now we want to do something like student smokes, yes, no, parents smoke, both, one, or neither. And we have some table of counts. And we have a total. So the key, sometimes to put this into the to put this into R SAS, you need to not write the no and express it as the successes and the totals. But that's just an implementation detail. But the key idea for how we treat multiple levels is kind of an obvious thing to do, which is if we have k levels, we create k minus 1 dummy variables. So this kind of is destroying all ordinal information, which is sort of unfortunate. But if there's ordinal information here, it's ignoring that. And it's just kind of what's sometimes called a one-hot encoding. Right? So in other words, we create a variable whose entire job, x1, is either 1 parent, 0 otherwise. So 2 parents or neither parents, which is a bit odd, right? And we have an x2, which is 1 if both, and 0 otherwise. So in some sense, all we're doing is saying whenever you have a multi-level table, you turn it into a more-way table that's binary.
So you're assuming that neither parents smoke. Like that's your baseline.
There's no baseline here. This is just.
When you create your model,
yeah.
Is that your baseline?
Yes, it will be my baseline. But this is not versus the baseline.
Yeah.
This is just versus one parent versus the rest of the world.
Yeah.
2 parents versus every other possible outcomes.
Yeah, excuse me. So I was wondering, here we're using k because we have k level, but the reason why we only have the k minus 1 is because the last level is going to be automatically detected.
That's right. Yeah. Okay, so then we get a model, log p 1 minus p, which is some intercept term plus a term for our first dummy variable plus a term for our second dummy variable. Right, so this is 1 versus not, and this is the 2 versus not. So last time I was talking about how we should think about these dummy variables as encoding events in the sense of probability. That's what they're doing. They're saying we have events, and I'm making no guarantee that these events don't overlap. Right? These events do overlap. Well, not the one doesn't, but the zero overlaps. I have no choice but for that to happen. Right, so this says the log odds of student smoking is B0 for neither, beta 0 for neither, beta 1, beta 0 plus beta 1 for 1 smoking, beta 0 plus beta 2 for 2. That's our encoding. And then we have x beta j is the conditional odds ratio for level j versus baseline. Right, because these are log odds. E to the beta 1 is the amount that are multiplied over this baseline. E to the beta 2 is the amount that the odds are multiplied over that baseline, over e to the beta 0. In other words, beta 1 is log odds for one parent minus log odds for neither. E to the beta 1 is odds given 1 divided by odds given neither, and so on. Is it clear what these coefficients mean? Beta 2, now let's say e to the beta 2 is odds for smoking, this is, right, of course, odds given both divided by odds given neither, and e to the beta 1 over e to the beta 2 is e to the beta 1 minus beta 2 equals odds given 1 over odds given both. Okay, so all of we have a 2x3 table. There's 3 different odds ratios. There are 2 free odds ratios, or 2 degrees of freedom. And we can obtain, given any 2, we can obtain the others from that. And so you can, again, in this case, by computing odds ratios in the 2x3 table, you can obtain all these coefficients by hand, and they're what you would expect, right? So like,
Yeah, I was wondering, are we using a normal way, say ordinary least square to estimate our
No.
data coverage?
no. Yeah, these are likelihood-based models. Okay, so beta 1 is 0.351. Beta 2 is 0.588. And beta 0 is minus 1.826. And these are the same as you would get if you had just computed the, n11 over n times n22 over n12 and 21. So given those coefficients, our full saturated model is logit p is minus 1.8266 plus 0.349 x1 plus 0.588 x2. So again, this one is 1 versus otherwise, and this is 2 parents versus otherwise. And this is the baseline. And so you get the probability of by inverting the logic, you can get the probability of the predicted probability of the student smoking. For example, P smoke given 1 is e to the minus 1.826 plus 0.349. Right, we pick up on that. We pick up in here the one that corresponds to one parent smoking divided by 1 plus e to the minus 1.826 plus 0.349 equals 0.1858. So if you need to recover the probability, you get it that way. So what's the g squared for this test?
Oh, I have a quick
Yeah.
question. So beta 1 is 0.351 or 0.349.
Oh, yeah, 349. Sure. So if I do can you tell me what the g squared or something will be for this? G squared or x squared would be? Hint, if I ask you to compute something like that in your head, it must be an easy answer, right? The answer is 0, because as a logistic regression model, this is saturated. We're allowing all the predictors. And you could test, so you could test this, so that your significance test won't make any sense here. Or your goodness of fit test won't make any sense. But you could get one that made sense if you eliminated some of the parameters, right? If you said, I'm only going to test one of these dummy variables, or I'm only going to test intercept only versus with both. Right, those things I can talk about. So for example, you could test a null intercept only. Which is zeroing out beta 1 and beta 2 versus alternative, this full model. And if you did that, you would get, that has 2 degrees of freedom because we've killed 2 variables between those 2 models. And the chi-squared, the g-squared would be 38, statistic would be 38 and change. And the Pearson, I think, is around 37. And so these are both very significant. So that would make sense to do. And this is a particular group of coefficients. I've chosen B1 and B2 versus them being 0. But I could take any subset and do a similar test. Right? So in other words, I could have some model, beta naught, beta 1, beta 2, beta 3, and so on, beta 4. I can pick any of these subset of these, zero them out, and compare their joint significance to the base 2 without them. That's all I'm saying. And that's just using the same kind of idea that we've been doing. We mentioned that because of the nature of these estimates being maximum likelihood estimators, the beta j are approximately normal with a standard deviation, which you can get from your computer. And so we can get confidence intervals, beta j hat plus minus our term times the standard error for beta j, which will get output by the test. And you can test each one individually. And that test should give you the same answer as the g squared in terms of whether or not it's significant. Nice musical interlude. But
yeah, I wonder, so in the context of the parents' behavior might have impact on the children's behavior. Suppose the result here, because the g squared is pretty large, so we're gonna say we're gonna reject the null hypothesis. So in the context of our problem, whether we can claim that the father's parents' behavior can have a huge impact on the children's behavior regarding to smoking, right?
Right. Okay, so the next, let's see, the next thing I want to discuss is the relationship between, yeah, sure.
So for the null hypothesis, that was at like the intercept only model. In the alternative, can we say then compare it with the full model? I don't think.
This is the full model. At this point, this is the full model.
I think if the null hypothesis is the beta 0 only model, then the alternative should be not like the only beta 0 only model is not fit. Probably like we have beta 0 and beta 1.
We're in violent agreement. I completely agree with you. I just claim this is the full model. Equals beta 0. Is that what you're saying? I'm saying this is the full model.
Yeah. But if we reject null hypothesis, we cannot conclude that that's like full model. Probably we have beta 0, beta 1. That will be the model. We don't need to have the full model.
Right. That's a different. So we have like beta 0, beta 1, beta 2. This is, let's say, not 0, 0, 0. Then we have this is not 0, this is not 0. Or this is not 0, this is 0, this is not 0. And then up here we have they're all not 0, which is like the saturated model. And all of these arrows represent tests that make sense, including this one. So we're just doing this one, but we could equally do either of these other tests. That make sense? I'm going to dig into this situation and how it relates to that hierarchy now. So maybe that will help. This is just kind of the Boy Scout example again. Well, let me do this example for the Boy Scouts, and then maybe we'll see if that helps or not. So you remember the Boy Scout table. Which is big, I'm not going to write it down again. And there's like marginals, delinquent versus Boy Scout, for example. This has a log odds of minus 0.614. And it has some standard error. And that says being a Boy Scout lowers your log odds of delinquency. The odds ratio is 0.541. And if we have a logistic regression version of this, this is log p 1 minus p beta naught plus beta 1 xi. So this is my dummy variable, 0 if non-scout, 1 if scout. I fit that with logistic regression, fit it with R SAS, and it will output beta 1 hat to be the same number, minus 0.614. Just log odds. If we do the 3x2 table, delinquent, yes, no, SES, low, medium, high, 52, 213, 34, 212, 236, 10, 255. How many log odds ratios do we need? We need 2. There are 3 there. We need 2. And then we have choice about which ones to do, right? Which is like different encodings of the table. Exactly map. So we have like the this one, which is 1.735, and we have the longer one, which is 6.375 odds ratios. And they have log odds ratios of 1.7.55 and the other one 6.3, 6.4 is 1.85. And they have some standard errors. So far, nothing new. But then to do the logistic regression, we're using, again, this sort of dummy variable system. So we have new dummy variables. X1 is SES equals M, and X2 is the event SES equals high. Right, so these are indicator variables for these events in probability space. And we can write down our model. Log P, 1 minus P, beta 0, beta 1, beta 2, X2. And then we get, and so beta 0 are the baseline log odds, the log odds of being delinquent at SES equals L, and then beta 1 and beta 2 are the multiplicative, or e to them is the multiplicative change. And if you do your regression, your logistic regression in our SAS, you'll get beta of, let's see, beta 0 minus 1.38, beta 1 minus 0.55, and beta 2 minus 1.85, which look different. And it's just because this one we want to flip this is like it's 1 if it's SES-M, and this implicitly was the other way around. So it just gets, so when you do this in the computer, you may have to take a reciprocal somewhere. That's the point. But otherwise, you'll get the same odds ratios. Okay. So now I want to explain how this relates to the hierarchy that we've seen. This one, which caused many annoyed faces at some point, I think. Okay. So let's say we have 3 variables, categorical variables, A, B, and C. And we have all these different, in log linear model notation, the different models that we could construct. A and B are jointly independent of C. A and C are jointly independent of B. And B and C are jointly independent of A. Right? So A and B are allowed to depend on each other. A and C are allowed to depend on each other. B and C are allowed to depend. Okay. Then the next level up is the conditional independence models, right? AB, BC, AC, CB, BA, AC. What's the next level? The next model up from that includes all of these models, but isn't saturated? Remember what that's called? I think I heard it. This is the homogeneous association model. And then above that is the saturated model. So that's our whole model hierarchy, and I'm not going to draw all the inclusions. Okay, so now how does this relate to logistic regression? Well, we take this model and we pick one of these variables to be a response. So let's say we say C is the response. C is delinquency. What does it do to this table? Does it simplify this zoo of models? Another way of saying this is, where do the coefficients, these betas, where do they show up in this table? Okay, so, well, how about the kind of the baselines? Baseline is sort of down here somewhere, right? The beta 0, the beta that only controls C. So let's say there's sort of a beta 0 or beta C, and that lives sort of down here, and it doesn't. Once I move, or you could say it lives at this level. I'm conditioning on C, that's kind of the only one of these that survives. Right. So the independence model, ABC, what does that say? It says the coefficient for A is equal to the coefficient for B is equal to 0. And our coefficient for C is allowed to be non-zero in our independence model. This is our beta 0. So in this one, so now we have the beta A and beta A and beta B may be non-zero. That can happen in this level, right? So how about this one? Which new coefficient am I allowing to be non-zero? So A and C are allowed to depend on each other. They're independent of B. C is what we care about. A, right. So we're looking at A and C being dependent. Right, so this one has beta A non-zero. How about this one? Beta B is non-zero. How about this one? Right, none of them can be, right? So this one, because we don't care, right, we're conditioning on A and B, which is sort of like saying we're doing a product multinomial sampling, or we're fixing A and B. We don't know anything about the relationship between A and B. We don't care about the relationship between A and B, right? So really, this model and this model are the same, right? Now go up another level into the conditional independence models. So really we should say here, okay, beta A or beta B at this level are non-zero. At this level, we can have both, right? We can have beta A and beta B non-zero, right? So here, this one is, okay, let's look at this one first. A and C are related, C and B are related. Both beta A and beta B are non-zero. A and B are related, A and C are related. What happens here? Beta A is non-zero, but we don't, we still have beta B 0. Right? So this is actually the same as this model. And in this one, B and C are related. A and B have some relationship allowed, but we don't care about that because that's what we're conditioning on. So actually, this model and this model are the same. Okay. And then here we have all of them. So this is and. Sometimes one of them are non-zero. Sometimes one of them is 0. And in this one, they're all allowed, right? So we have beta A, and here we have beta B. And this one we don't care about. So this is, but this tells me this one is actually equal to this model. And up here, if it makes sense, we might get another coefficient beta AB. Because now AB are allowed to jointly depend, or C can jointly depend on AB. We haven't really talked about what's going on with that yet because all our examples so far, that's impossible, right? Our dummy variables were mutually exclusive. So x1 times x2 is always equal to 0. But if x1 times x2 is not equal to 0 for these things, then we need a new coefficient for the possible interaction. Right? If there's a failure of homogeneous association, that means that the influence that, say, B has on C could depend on the level of A. And that means there's another model up here. So this is beta AB, beta A, and beta B. All possible at the saturated level. So if you think about this as like a partial order, what we're doing is we're taking kind of a quotient. We're dividing by the relation. I don't care about whether A, B are related or independent. If they're joined together or not, doesn't matter.
Yes, excuse me.
Yeah.
I was wondering, so for our hierarchy model here, we're only interested in the main interaction, right? So we do not care about the two-way main interaction or even higher.
Well, we may care about the interaction. We may care about this interaction, yeah.
But only two factor interaction, not the three.
Yeah, well, I mean, this argument works for any number of variables. I'm only just doing it with 3. So let me do it. I'm going to do it again now in a way that's not quite as hard to look at. Okay, so let's make a cube. This is a cube, secretly. And if I had more than 3 variables, it would be a hypercube of some dimension. Okay, so here I'm going to put the model A, B, and C are all independent. And here I'll put here I'll put the model A, B, C. So A and B are allowed to depend, and they're independent of C. And so I could think about this as being in 3-dimensional space. This is a direction which is the join A and B, or allow A and B to interact. Okay. Up here I'm going to put A, B, C. So the up direction is join BC. And then here I'll put AC, B. So the into the board direction is join AC. Okay, so following that rule, to find out what this one has to be, it's either I take AC and I join AB. So now I'm allowed AB and AC, which is consistent with starting here at ABC and joining A and C. So I have AB, and now I have also AC. Okay. And similarly, I can figure out what this one is. So this has to be AC, BC, because I go from ACB, and I go in the join BC direction, or I go from ABC, and I go in the join AC direction. So this is the second level of the hierarchy. And this one will be AB, BC, because I start from the ABC and I go in the join BC direction, or I start from ABC and I go in the join AB direction. And then at the top of the hierarchy for the cube is the homogeneous interaction model, AC-BC, and the saturated model is somewhere out here. Okay, so now what does it mean when we condition, as we did over here? So I said it was some kind of quotient. Okay, so if I condition on AB as a joint variable, that means I project. What do? I take the direction join AB and collapse it. So the equalities that I wrote over there, which models are the same, are just models that are separated by adjoining AB, because that's what we're conditioning on, are the same. So these two models are the same, these two models are the same, these two models are the same, these two models are the same. So what we're left with is a square, or a hypercube of one less dimension, if we have more factors. And we've identified those variables. So we're left with a square that looks like this is either A and B, C are independent, or A, B are jointly independent of C. This is A, B, C, or A, B, B, C, and, so these two models are equal. This one is ACB, ABAC, and this one is ACBC, or ACBC, AB. Okay, so that's the story of how these things relate and what happens when we move from an arbitrary log linear model or an arbitrary hierarchical model to a conditional version, a logistic regression. All of the coefficients that correspond to the things that we've collapsed away disappear, because we're not interested in them anymore, and we're just left with these sort of equations, equivalence classes of models. Okay, so let's get back to the Boy Scout table. So we can fit lots of different models to that table. As a multinomial thing, we can fit all of these different models. As a conditional thing, we only have 4 choices. Well, 4 choices plus the saturated thing. Right? I forgot to put the saturated. The saturated goes A, B, C up there. Right? So, we have models, logistic regression models, log P over 1 minus P. So our simplest one is that one. Which model is that in this square? It's this guy, right? The independence one, or the one where these two depend on each other, but we don't care. We can add on a dummy variable. Is this person a scout or not? Which one are we? Well, I guess I should have. Let's make a. What is it, A, B, and C? I guess C is. Let's say A and this is scout, and B is SES. Well, that only works if it's binary, right? So when this becomes non-binary, we use the dummy encoding. We have to pick up another dimension. So we're going to get a cube, kind of. Okay, so when we add another variable like this, scout, now we go up to a more complex model, like this one, depending on scout. Then we have to go to the next model, P 1 minus P beta naught plus beta 1 x scout. And then we have these dummy encodings, beta 2 x medium plus beta 3 x high. So this one is, this is the sort of the 2x2 scout marketing table. And this one is the conditional independence one, right? This says that, oops, sorry, that's not right. That is the conditional independence one. This is B is independent of D given socioeconomic status. So this says that the whole effect is due to socioeconomic status and there's no effect due to scout, whereas this says the opposite. This is all about scout and not about the other one. And then we have the full model. Do you want to do it? No. So let's do this next one that has main effects for both. x1 plus beta 2 x2 plus beta 3 x3. So this is the, we have main effects for both. Okay, so this is like both A and C are allowed to, this is up here. This is a homogeneous association. In other words, both scouting and SES are allowed to affect delinquency, but there's no interaction, right? So they have this, that's another way of saying they have the same, you know, these coefficients, beta 1 and beta 2 are not affected by x1, or beta 1 is not affected by x2, x3, is homogeneous association. It says the effect of scouting on the outcome does not depend on this other factor. If these are 0 or 1, this coefficient doesn't change. So that's why it's homogeneous association. And then I have the saturated model. Which does have that term. And because I have 3 levels, I get 2 coefficients for this model. If I only had 1 level, I would only need 1 coefficient, but I have 2 dummy variables for SES, right? As far as this logistic regression is concerned, it doesn't know that it's even a 3-level variable. It's just made it into a 2 by 2 by 2 table, 2 by 2 by 2 by 2, 4-way table, right? So with a special constraint that of this mutual exclusivity, with the exception of mutual exclusivity, it doesn't know. Okay, so then this is the full model. This allows for interaction between whether you're a scout and what your SES is through these 2 coefficients. And those are the new coefficients. So we're building up, you know, conditioning on C, or conditioning on AB, conditioning on scouting and delinquency. We can build up we can climb up this hierarchy of the models, this R slice of a hypercube, by adding in more of these parameters. At each point we can get a significance test, we can get a G squared, a delta G squared for how valuable it is to add in these things. So that means that, for example, you know, when we can go from this one, so these 2 can't be directly compared, but they can be compared above the baseline model of just beta naught. What we can do is say, take this model, B is independent of D given S, is a conditional model, and compare it to this one. And we can say, once we take into account SES, if we also add in a main effect for scouting, is our model significantly better or not? Right? We'll get a delta G squared here. It'll have 1 degree of freedom. And our hypothesis, based on the data, should be that that change is not significant. And if you run it, that's what you'll see. And similarly, you know, we can do a test from this one or from this one up to this one that includes the interaction effects, and we can judge whether the interaction effects give us significantly more power or significantly more understanding of the data.
Yeah, excuse me. So I was wondering the way how we just propose our model, whether it can be reversely. So whether first we have to say propose our full model, and then we say if we reject our, we fail to reject our hypothesis, and then we can go for our reduced model.
It's a very open-ended question, so you can go in both directions. In fact, they have names, so if I start from the null model and I increase, it's called forward selection. If I start from the full model and eliminate things, it's called backward selection.
Yeah, sure. So what's the criteria for us to select the model, whether it's based on the AIC or using the BIC?
Yep, you can do it using those. Right, we're not talking about that yet. But. Right, so if you want to do this in a principled way, of course, you should give some kind of score for complexity, some cost for the model of complexity, because more complex models will always fit better A way which is not as formal but works pretty well is just to do this kind of go up until the gain is not significant, right? Or take the shortest path up from the boring model, from this model, go up until you get significance. Of course, there may be a situation, as in this one, where you have two choices, right? You get a small gain in significance, a large gain in significance, or you can go the other way and get a large gain in significance and a not significant gain in delta squared. And in that case, you'd want that model. And that's what happens in this example. So let me. So let's write that down. Actually, there's a table here. So g squared, degrees of freedom, p-value, saturated, s plus b, s b. G squared, of course, for saturated is 0. For SES and Boy Scouting, it's 0.15. So it's a very 2 degrees of freedom that has 0 degrees of freedom. 928. This is 0.16, 3.984. This is 28.8, 4 degrees of freedom, and null, which is intercept only, 36.4, 5 degrees of freedom. The p-value is 0. Okay, so this says the null model doesn't fit. These two models fit. But the difference between these two models is only 0.01. And if I go this way, okay, this doesn't fit either. Now I add an s, it looks great. But if I go the other way, I start at the null, I go to scouting, and if I go up here, the gain in fit is not significant. So it's this picture. And so for this, would say that the rule would say, okay, so you should choose this, not this model. Yeah, sorry.
What is each compared to? What is each model compared to?
What is each model compared to? Beta naught, S, B, S plus B, sat. So any path in this graph is a valid comparison and has a g squared and a significance associated, a delta g squared and a significance associated to it.
So is it possible for us to choose a path which is diagonal path, instead of path, move along the line? The side can we just, what is possible? For us when we choose the model, basically we're using the beta naught when we jump to the s plus b, go for the diagonal path. Is that possible? Because here
I don't understand. Any path. So that means that if you can go from here to here and here to here, you can also go from here to here. So a path is a sequence of edges that
so how about the diagonal? Can we just jump, kind of a jump?
Yes.
Okay, so if you're trying to estimate s plus b, how does that happen that if you compare it to s and you compare it to b, that it gives you the same answer? Because it won't be an equal improvement.
Right. Okay. So let me put these numbers in. Okay. So this is null. Going from null to b, the delta g squared is 7.6, and the p-value is 0.006. Going from null to s, the delta g squared is 36.25, and the p-value is 0, or approximately 0. Then going from s to s plus adding b to the S model. So going up here, the delta G squared is 0.01, and the p is large. And going from b to S, I think I maybe don't have that one. Well, we can figure it out. Going from b to S is going to be 28.65. So those are the numbers we want to look at. These are the delta G squareds. And if you think about it in terms of this cube, we want the directions that are big. So this direction is big, this direction is weak. So let's just stick with this direction. Yeah.
I have one more question for the model selection. So if you compare the delta G from S model to S and P model, the delta G is only like 0.01. So that means adding B variable is not significant.
Right.
So we can choose the S model.
Yeah, but yeah, that's right. That's supposed to be the conclusion. Yeah, that's right. So S, this is unfortunate notation. So S means SES, B means scouting, right? Boy Scout, yeah. So what we're saying is that the values on this cube or these things suggest that, of course, the S plus B model is always going to be better than the S, but it's not significantly better. And so we should just stick with the simpler model S. And you can guess from this that, these other criteria, AIC, BIC, WAIC, and many of its relatives amount to, you take these delta G's and you correct it by some complexity score cost. Right, so you penalize the gain in delta G for the gain in model complexity, and that allows you to, in an automatic way or in a formal way, trade off between those and make that decision without having to make the call yourself.
Yeah, excuse me. So related to first question, so when we just, if we consider about the BSA and ASA, can we also consider about the principal component, like say, because we know that.
Yeah, I don't think principal components would make sense here because this is we're talking about categorical data.
Yeah. That's a form continuous.
Yeah, that makes more sense for continuous sense. Okay, so I will stop there and we can ask questions and stuff. Go ahead.
In the